Hey everyone, welcome to Duodecimal Division. My name's Eric Larson, and in this video I'm going to be revealing to you the base 12 version of pi. So I'm going to give you what all those numbers are, but before we get to that, I just want to go over the structure from which that number emerges so we really understand what those numbers represent. So we're going to start again looking at this pattern here and just go over the difference between base 10 and base 12 one more time and how the difference lies in the dividing up of the 1. So here we're looking at the circle, the circumference of the circle. We know that the value of the circumference of the circle, or the formula for, is 2 pi times the radius. So when we give the radius the value of 1, the whole circumference, let's say this inner circle here, has the value of 2 pi. So half the circle is 1 pi. And in base 12, because we've now divided these lines, there's 12 of these sections, we can give the value of pi a decimal version that lines up. We can say this section here is 0.1 pi, 0.2. I can count from here very clear then, 1, 2, 3, all the way, and this 1 pi, these lines going out line up exactly with the places where we have 0.1 pi, 0.2, 0.3 in base 12. In base 10, it's a bigger unit. We have, instead of 12, we have tenths. A tenth is a bigger unit than a 12. So our units of pi are bigger and they don't line up on these same points. So that's why we have to refer to these sections as pi over 3, pi over 6, pi over 4, pi over 3, etc. Because that way we can still use those points on the circle, which are very important and relevant, but we don't have the access to, say, 0.1 pi, 0.2, 0.3. Okay, so now I want to show you how do we find, if this is 0.1, the 15-degree line, how do we get to 0.01? How do we divide that section up into the decimal version of pi? Basically 12 more little sections again, 12, but in base 12 it's 10. Okay, so now I'm going to show you because it has to do with the base 12 dodecagon. So again, it's the same thing. There's a pattern. It's a type of dodecagon. In base 10, it doesn't line up the same way as it does in base 12 with the 1. Just like in base 10, this pattern doesn't line up with the 1 in the same way. In base 12, it's perfectly fits together. So the same thing with the dodecagon I'm going to show you. In base 12, it lines up with the 1. It lines up with the circle. Everything fits together just like a lock in a key, or a key in a lock, and that doesn't happen in base 10. That's why you've missed all of this geometry. So I'm revealing to you, it's like a door that opens up into a whole new way of looking at the geometry of the circle. This is what the base 12 version of the dodecagon looks like. Okay, so just first of all, if you're new to this channel, and this is the first video you've ever seen of me explaining all this, this is what the pattern looks like on the grid without any defining lines for the base. You can see there's an x-axis and a y-axis. And this is the dodecagon, or actually it's a series of dodecagons. So we're now going to look at the inner dodecagon, the first version of the pattern in the series. And we're going to again look at it on a base 12 grid. Okay, so here is the inner ring of that series of dodecagons, the first ring in the series, the smallest one. So I've blown it up. We're looking at larger scale graph paper still. So first of all, base 12. So we're committing to base 12 now. We've got a grid, base 12, 0.1, 0.2, 0.3, 0.4, all the way to 0.8, 0.9, point A, point B, and then 1. So just to be clear, A and B are going to be the numerals for the numbers between 9 and 10, or 0.9 and 1 in base 12. Okay, so first of all, it's coordinates, the coordinates of each of these points. So here, this point here is 0 on the x-axis and 1.1 on the y-axis. Here we're at 0.7 and 1, so go over 0.7 and up 1. Here it's 1 and 0.7, going over 1, up 0.7, and here it's 1.1 and 0 on the y-axis. Okay, so that's the same all the way around. So the length of the sides are all 0.5 root 2. You can see down here I've drawn a little right angle triangle, 0.5 root 2. So this side also is 0.5 root 2, and I've used the Pythagorean theorem just to prove that and show you some base 12 math. So 0.7 squared is 0.41 in base 12. 0.1 squared is 0.01. So 0.41 plus 0.01 is 0.42. So this side here is the length of the square root of 0.42. So we can test and see that 0.5 root 2 is that the same, while 0.5 squared is 0.21 in base 12. So 0.21 times 2, or square root times square root, is the square root of 0.42. So therefore the 0.5 root 2 is the same as the square root of 0.42. This number is going to be coming up a lot in the math to come, as is this number here, or these numbers, 0.7. The hypotenuse of the triangle that's formed here between this point, and that point is the square root of 1.41. Okay, and another number that's going to be showing up again and again is this one here, the 0.96 root 2. So that's the length of this line here from this center point of the dodecagon to the point where the 45-degree line crosses the dodecagon up here. So again, square root of 2, square root of 2. We're going to be working in units of square root of 2, and we're going to be working in units of 0.96 root 2 and 0.5 root 2. These are the base units of the entire diagram to come. So again, we're going to be looking at how to, first of all, build the diagram that generates all 360 degrees, so we really understand how that works. And then we're going to use that diagram in the model that we've created to come up with the base 12 version of pi. Okay, so that's what all that looks like. Now we're going to look at the relationship of this triangle here to the special right triangle with the angle of 30 degrees. Okay, that's also very important to realize what that relationship is. Here we go. Okay, so here we have three triangles. The top one is the familiar special right angle triangle with the dimensions of 1, 2, and the square root of 3. Here's the triangle that we were just looking at in the dodecagon with the sides of 0.7 and 1, and then the hypotenuse was the square root of 1.41. So in order to see what this triangle looks like when the bottom is 1 in relation to this triangle, we're going to divide all the sides by the square root of 3. So square root of 3 divided by the square root of 3 is 1. Square root, or 1 divided by square root of 3 is square root of 0.4. So like in base 12, again, 1 divided by 3 is 0.4. So that's how we get that. And then that works out, square root of 4 divided by square root of 3, square root of 1.4, which is the same as a squared plus b squared equals c squared. So we can see here, this length here of 0.4 and 0.41. So this length, this triangle here, is a little bit bigger than this one down here, than the 30-degree angle. So we can see this line here is going to be a little bit higher than the 30-degree angle. So now we're going to go back to our dodecagon. I'm going to show you a blown up version of the relationship between these two lines, what that actually looks like. All right, so here is the large scale version of the relationship between those two lines. We have a big square of 1 by 1. Top line is the dodecagon line, where it's intersecting the dodecagon at this point here, has the coordinates of 1 and 0.7. And then we can see the 30-degree line coming up underneath it has the coordinates here of 1 and square root of 0.4. And so I worked out square root of 0.4. The first few digits are 0.6b, 17b, 27. So a real base 12 number. Again, 12 little squares inside each of these sections. So from here we're going up 1, 2, 3, 4, 5, 6. And then inside that square, that's 0.6, and then 0.0, 1, 2, 3, 4, 5, 6, 7, 9, A, B, right? And then 1. So that's what that looks like. Again, base 12. Okay, so now what we're going to do is go back to a smaller version of the dodecagon, the series of dodecagons, and we're going to start to build the diagram for 360 degrees. We're going to go to the fourth ring of the dodecagon. That becomes the first ring of our 360 degree diagram. Okay, so here we are, the smaller version of the dodecagon. We're going to the fourth ring in the pattern, and we started the process of dividing the diameter into what's now the perimeter of the dodecagon but will ultimately become the circumference of our circle. And just reminding you, we're working in base 12, we're working with a dodecagon that we've never had access to before, we're working in units of square root of 2, so this is all very new in terms of the proportions of the sizes that we have to work with. So I'm going to put my clear board up there with a lot of mathematical information regarding all the lengths of these lines and the diameters and radiuses of the circle and whatnot. And we'll just take a look at what this looks like mathematically. Okay, so first thing is, what exactly are the perimeters of these dodecagons as we go larger and larger? Well, the first one, remember, is in units of 0.5 root 2 each section. So there's 10 sections in total in base 12. So 0.5 root 2 times 10 is 5 root 2. So that's the total perimeter of that inner dodecagon, 5 root 2. So then the second dodecagon is 2 times that. So 2 times 5 root 2 is a root 2. The third dodecagon is 3 times that. So 3 times 5 root 2 is 13 root 2. Then the fourth dodecagon is 4 times that. So 4 times 5 root 2 is 18 root 2. So now we're going to do the same thing with the diameter. So the again, the radius, or half of the diameter at this point, is 0.96 root 2 from the center to that first section of dodecagon. So 2 times 0.96 root 2 is 1.7 root 2. So that's the total length across the diameter along that unit, 45-degree line, square root of 2. So 2 times 1.7 for the second ring is 3.2 root 2. The third, 3 times 1.7 root 2 is 4.9 root 2. And then 4 times 1.7 root 2 is 6.4 root 2. That is the total length of the diameter for the fourth ring of the dodecagon. So now what we're going to do is divide the diameter into the perimeter. So 6.4 root 2 into 18 root 2. 3 times 6.4 root 2 is 17 root 2. So 3 times, and we have a remainder of 1 unit of the square root of 2. We're just going to leave it there for now. So 3 times this section, now we've got 8 of these units, or 8 of these circles, so 8 times 3 is 24, speaking in base 10 now, and we've got 12 sections, so 24 divided by 12 is 2, so we got 2 of these circles are going to fit into each section of the dodecagon. So what we do now is to put them up there and to place them in the exact right spot. And remember, again, we're using all lattice points up here. Everything is actually very precise. So what we're going to do, this particular section of the dodecagon is 4 times 0.5 root 2. The total length is 1.8. Remember, the whole length is 18, so 18 divided by 10, 1.8. So we're going to start in the center, and we're going to count over 0.5, 0.1, 0.2, 0.3, 0.4, 0.5 root 2. Put a point, I'm going to set a compass to the radius of these circles. So the radius, the diameter is 0.96 root 2. We're going to divide that in half. Divide it by 2, we get 0.49 root 2. So we set compass to 0.49 root 2, put it down there, and draw a circle. So the distance from the circumference of this little circle to the end of the dodecagon is going to be 0.5 root 2, subtract 0.49 root 2, have the answer or the result of 0.03 root 2. So there's a little gap here between the circumference and the end of the line. There's a gap here between the circumference and the 45-degree line of 0.03 root 2, and that's the same for this other circle on the other side. So we have 4 gaps along that dodecagon line of 0.03 root 2. So 4 times 0.03 root 2 results in 0.1 root 2. Then what we're going to do is repeat that pattern for all of the sections of the dodecagon. So 0.1 root 2 times 10 is 1 root 2. So everything's lining up, but the question now becomes, how do we get our next 2 circles positioned down here so that the relationship that these circles have to the 45-degree line is the same down here to the 15-degree line. We want everything to line up and balance perfectly. So that's the next thing I'm going to show you, is how we take this information here and get the exact same result down here. So the relationship of these also to the 30-degree line, how it's just a little bit inside, is exactly the same down here also. So just put my whiteboard behind so you can see all that if it wasn't clear. Okay, that's what that looks like. Now I'm gonna show you the process that we're gonna use to convert all that information from one section of the dodecagon to the other. Okay, so here's the same dodecagon pattern, and now I've included this pattern inside here as well, just to remind everybody that we do have a 15 degree line, 30, 45, and that those degree lines are generated from this geometric pattern in the center here. So that would be the first step in this entire diagram, would be to draw this, establish our 15 degree sections, and then we would work off the dodecagon after that. So now what we're going to do is draw a circle, a large ring at this point here, using this lattice point where the 45 degree line is crossing the dodecagon. The radius of that circle is going to be 4 times 0.96 root 2. Then we would go to the point that we just determined for placing this small circle, and we would draw another large ring with that being our radius. And once we've got those two circles established and both of them are crossing the 15 degree line, then I would set my compass to 0.5 root 2, that exact length there. And I would put it down on the inner ring on the 15 degree line, and I would make a mark on the outer ring on both sides. Then I would reset my compass to the radius of this circle. I would place it on the point that I just made and draw those circles again. So now these circles would have the exact same relationship and position to the 15 degree line as these circles do to the 45 degree line. Okay, so the radius of the first circle that we draw is 4 times 0.96 root 2, which is 3.2 root 2. So 3.2 squared is a.04. Square root of 8.04 times square root of 2 is a square root of 18.08. So again, that's the radius of our first circle. Then we're going to add length to that radius by adding 0.5 root 2 at a 90 degree angle. And so that length is going to be the square root of 0.42. Remember, 0.5 squared is 0.21. 0.21 times the square root of 0.42. So we have a Pythagorean triangle forming here, right angles. So a squared, 18.08 plus 0.42, c squared is 18.4a. So square root of 18.4a is the radius of the second circle that we draw. And then again, we put the compass on the inner circle, continue that pattern. That's how we place these two circles here. So we do have a gap now between these two circles. The original pair that we had, there's a gap of 2 times 0.03 root 2. So that gap in between them is 0.06 root 2. So what about this gap here now that's been created between these, sort of the sides of these pairs, between these two circles here? Well, we know, again, the total length of the dodecagon that we started with was 18 root 2. And we know that the total length of all the diameters of these smaller circles is 17 root 2. So 17 from 18 is 1 unit of square root of 2. That was the total empty space that we started with, that we're working with. So when we add up all the empty space between these pairs, that's 10 in base 12 times 0.06 root 2, which is 0.6 root 2, which is half of our total. So the empty space that we have left is still 0.6, and there's the same amount of gaps still to be accounted for. So of course 0.6 root 2 times 10 equals 0.6 root 2 divided by 10 is 0.06, basically the same amount. So we can see that the gaps between these two circles is exactly the same as the ones between these circles. So the sort of the edges of the pairs is exactly the same as the gap between the pairs. So that's that. So what happens is now we join a line between, or draw a line between this circle and that circle. We create an angle between this straight line and that straight line there. So what's the angle that's been formed between all of these circles, or the angle inside of all of these little circles? Well, there's a formula for figuring that out, because basically we've created a polygon. Although it is made up of two different elements, they are all in line with each other. So we have a 24-sided polygon, or 20 sides in base 12. So here's the formula: n minus 2 times 130. That's the base 12 version of 180 divided by n. N is the number of sides in our polygon. So the base 12 version of that equation, 20 minus 2 equals 1a. 1a times 130 is 2360. 2360 divided by 20 is 119. So this angle is 119 degrees in base 12, which is 165 degrees in base 10, just so you sort of know what that works out to be. Okay, I'm just going to put my whiteboard behind so you can see all that clearly. If you can't already, there you go. And now I'm going to show you that same diagram completed, drawn as best I can to proportion. Okay, so here's that ring all done to perfection, looking very symmetrical. And you can see there's one more step that we had to do, is to put a circle around these pairs of circles. And actually that circle has the diameter of the section of dodecagon that it's sitting on. So the diameter of this circle here is 4 times 0.5 root 2, which was, remember, 1.8 root 2. So the radius was A root 2, which is, 2 times 0.5 root 2 is A root 2. Okay, so that's the dimension, and that's the actual unit that we're working with in terms of our diagram for 360 degrees. Each ring is going to be built in units of this ring right here. So here you can see there's 12 in total, speaking in base 10, and one of these rings is sitting inside this 30-degree section. So the next ring is going to have 2 of these sitting inside that same 30-degree section, and then 3 and 4 and so on. So we're going to take this diagram to a point where we have 30 rings, and the 30th ring has 15 of these sitting in, or 30 of these sitting in the 30-degree section. So basically each of these rings is a 1-degree section of the diagram. So at the beginning of the video, I posed the question, how do we divide up this 15-degree section, this 0.1 pi on a circle with the radius of 1. So that's what we're going to do now. We're going to find out where we can get, basically, again, in base 12, this is 13 degrees, not 15. So we're going to look for the degree line, which is 1.3 degrees. Okay, so I'm going to show you a picture here of a diagram that I built, or a construction of this diagram. I built this last summer during COVID. So this is the diagram that we're going to look at now. We're going to go to the appropriate ring in the series and find where we've divided up the circle into 1.3 degree sections. Okay, so here's the first panel in the series on the bottom. This is the circle that we were just looking at. I'm just going to go over quickly the process that we're going to use to create each additional ring. Basically, it's the same process that we just used creating this ring, where we are now working in units of 0.3 or 3.2 root 2. So 3.2, so we go another 3.2 to this ring here. So the inner ring, which is the defining ring of our diagram, is going to have the radius of 6.4 root 2. So we find that point, the lattice point, we draw a circle. Then we add 0.5 root 2 at a 90-degree angle, create the second ring with the slightly larger radius, and then we draw that ring. So we have 2 circles again to work off of. Then we use the degree lines that we've already have established, and we find the points for the circles on either side, and then we draw them on the outer ring. So that's how we just keep generating circles. And as we progress, the spaces get bigger, and we always are finding midpoints between either the degree lines or the circles that we're drawing, or that we draw them and then find new midpoints. So it's a combination of finding midpoints, drawing circles, finding new midpoints. That's the process for each ring. It's always a different combination of those procedures. Okay, so here we have the third ring, and here we generate the fifth, the 5-degree sections, and half of 5 is 2.6. Then half of 2.6 is going to be 1.3. So there's our 1.3, but we're not there yet. We're only on the third ring. So one of the patterns in this diagram is that when you generate 1 degree line at one section, here we are on the third ring. So another 3, so the 6th ring, we're going to see that this line here, the 2.6 degree line is going to be up here. The 5 is going to be up here. I'll show you that right now. Okay, so here's the next panel in the series, and here's the 6th ring in the series. We use the same process to establish the 2 rings. Then we go off the x-axis and we can mark the spots for this circle. We draw it. The center of that circle is the degree line for 1.3 degrees. So that's how we position that line or find that degree line. There's the 13 degree line at the top. So if you count down all the different little rings that we have there, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, 10. So we're dividing it into 12ths. You can see how that all lines up. So we found that particular degree line in the diagram. Now what I want to do is go to basically the end of this diagram, or of the drawing that I've done so far. We're going to go to the 15th ring and look at the circumference of the circle at that point. That's halfway to the fully completed diagram, but I want to just look at that and see what's happening in the circumference at that point and what's going to keep happening. And again, we're going now to the definition of pi, or the model of pi, the geometric model that is emerging from all of this geometry using the base 12 version of the dodecagon and base 12 and using the square root of 2. Okay, so now to the circumference of the circle. Okay, so here we are at the circumference of the diagram so far. And the main thing that I want to point out is simply what's happening with our diameter. So remember, these small circles were originally our diameter, and they were all touching each other in a solid line that made up the diameter of the circle. So now they're in the circumference of the circle, but you can see that they are separate from each other. There's an empty space that's between them, and that empty space is evenly dispersed throughout the entire circumference. So that's the real difference between this model, which is now a model that's emerging for pi, and the actual circle. We've only gone, 15 rings, 30 rings, but imagine if we keep going and going and going, millions and billions of, iterations of this pattern, we eventually get to a point where this line, that section of circle, is going to look like it's straight up and down. And when you get to that point, we basically have a straight line that has all this empty space between it. And so I think this is a better model of what reflects the nature of reality, in that there's a lot of empty space when you go into the very, very small. And our current version of pi is dealing with this idea of empty space, but instead of having it dispersed throughout the entire circumference of the circle, it's all just bunched up at one end. And so we have, millions and billions of digits that are just keep being added, but you can't really fill that empty space. So it's a different model, and it doesn't really reflect the world we live in. It comes from a place where, a long time ago, we didn't really know that there was empty space within the material universe. And so this idea of having a broken line didn't really make any sense. But now we know that the quantum realm, the atomic realm, has a lot of empty space in there. If we were to go, inside of a stick or basically anything, the empty space, again, is dispersed all the way through this line. It isn't all bunched up at one end. And so this geometry is revealing to us how we can see the relationship between the solid and the empty. I'm using those terms. I think they're the simplest ones to convey that there's basically just two aspects to reality, and pi does reflect that. Pi is a part of the equation of the standard model that's used to reflect the physics of the universe. I think this is a better model. So now what I'm going to do is give you the number pi, the base 12 version, and we get it by simply doing the equation that we started at the beginning of this video. Is take the center diameter of the dodecagon and divide it into the perimeter of the dodecagon. We can do it at any point in this process, but we'll go back to the beginning. I believe it is 1.7 into 5, or 1.7 root 2 into 5 root 2. That was the original version. Let's do that equation, and let's find out what the version of base 12 pi is. Okay, so now we're going to do the equation to figure out the base 12 version of pi according to the geometry of the base 12 dodecagon. So we're dividing 1.7 root 2 into 5 root 2. So we're going to convert those into complete square roots. So 1.7 squared is 2.61. So square root of 2.61 times square root of 2 is the square root of 5.02. 5 root 2, we've been doing this one already, so we know that it's the square root of 42. So 5.02 into 42, we're going to move the decimal over twice, so we get 502 into 4200. So we put our decimal point up above. Now again, these are all square roots, so our answer is going to be a square root, and it starts with 9. So that's a step in the right direction. So 9 times 502 is 3916. We subtract that from 4200, we get 4a6. We bring down the 0. B times 502 is 471a. Subtract that, we get 342 is the answer. We bring down the 0. 8 times 502 is 3414. Subtract and we just get 8. So 502 doesn't go into 8 0 times, so we bring down another, or we bring down a 0, doesn't go into 80. Bring down another 0. 800 is once. 1 times 502, 502, and on it goes. So what happens? First of all, that's unique in base 10. We can't do such a simple equation. One of the qualities of base 10 version of pi is that we can't do this, but here we are doing it in base 10 or base 12. So what happens? Well, we continue this equation for 96 iterations. That's a base 12, 96. So just first I'm going to comment on the fact that we've been using 0.96 in our dodecagon, the spaces between the different rings of the dodecagon was 0.96 root 2. So then we get a number that goes for 96 digits. It goes 0 at the end, and then it repeats. So that's the answer to this equation. And what I'm going to do, actually, I've done it here. I've got it written out on a piece of paper, and I'm going to stick it to the board here and just pan it so you can see the actual number in its complete length. You've come this far, you deserve to see the whole number. And then what I'm going to do after that is we're going to do the same equation, but we're going to knock off the square roots of 2. And we're just going to say, well, what's 1.7 divided into 5? Because that's also an interesting number, and it doesn't go on for so long before it repeats also. So we get a different type of answer, a different type of equation that's sort of breaking all the rules all the way around. But I believe, again, that it gives us a better version. It gives us that geometry that we didn't have before. So that's what I'm going to do for you right now. Tape this on the wall and show you the number base 12 version of pi. Okay, so first of all, if you're still watching this, I want to thank you for sticking around for this long. And really, I just noticed at my clock, it's 11:11 p.m. I've been working on this particular video all day long, and I'm pushing through because I got to go back to work tomorrow. This is the point in the video where you start to wonder, what am I watching here? Is this actually, in a way, history, unfolding in front? We got a new version of pi that maybe is the answer to the physicist's, dilemma about, quantum gravity and dark matter, because I think it is. Or is just some guy in his living room taping graph paper to a piece of plywood, making some sort of delusional video. Okay, well, the question's up to you. I believe this is the right version of pi and that it's important, and that's why we're here. That's why I'm here making this video. I'm sharing this information with you. This is what it looks like, math discoveries. There's a rawness to the whole process. So here we go. This is the base 12 version of pi as it comes from the base 12 dodecagon. So I'm just going to pan it for you. I'm going to shut up, give you a moment of silence with this number, and then I'll come back and we'll just wrap this up. Okay, we'll just just take a look at this number here, which is all this effort's been made to get it this far. Okay, kind of zoom in a little bit. Okay, I'm not going to read it out, but you can see I did all the iterations of multiplying 502. So there it is. So you can see that. You can do this yourself. If you want to, it's pretty straightforward. Download the base 12 calculator into your phone. Okay, I know it's almost too much, but here's the last part of this video. 1.7 into 5, so we swing that decimal place over. 17 into 50. We're starting with a 3. 3 times 17 is 49. Remainder of 3, we bring down to 0. 1 times 1.7, the remainder is 15. A times 17 is 13A, so from 150, here it goes. That's what it looks like. Down here, we get back to 50. So not the square root version of pi, is 3.1a, 8a1, 31a, 8a1, and that repeats. And I'm not going to say it repeats forever, because ultimately we only need it to go as far as a number that when we square it, then we get the version of pi that I just showed you, which does end. So this doesn't necessarily go on forever. It probably also goes on for, maybe it's the same amount of numbers. I'm not really sure how that works, but this squared equals 9.B80171, the number that I just showed you. So that's how that all works. We know, in math, a lot of times we're squaring pi or finding the square root of pi. So we already know what that is. We have those numbers. Again, pi is part of the standard model. The Planck length, pi is 2 pi. I can give you that number also. It starts at the square root. Again, basically 4 times 9.B801. 2 times that, square root of 2 is 4. So square root of 4 times square root of 9.B801 is the square root of 33, and that number goes on. That's the 2 pi. That relates to the Planck length. So again, we're talking about the smallest place. That's where we go. That's where pi, when you divide up all those numbers and keep getting smaller and smaller, that's where you end up. So the fact that it stops is a good thing. It doesn't go on for million, billion, trillion digits. That makes no sense. That's too small, and it doesn't have any structure. There's a lot of interesting patterns in that number, and there's all kinds of things to explore. And again, I certainly shouldn't believe that that's the right number that has a lot of solutions to physics problems. Okay, so now I'm maybe going too far. So basically that's it. So I hope you liked the video. Thanks again for sticking around. I'm going to put some links on here to other things. There's more information about that 360 degree diagram. Obviously somebody knew about that before. That's why we inherited 360 degrees from the past. That culture also generated or designed our numerals. So if you look on my YouTube channel, you're going to find a whole bunch of videos, one for each numeral, and explains why they look the way that they do. So this whole subject of base 12 math is actually huge, and there's a ton of more information squaring the circle. And now that we have this empty space to work in, it changes everything. Okay, so again, if you watched this far, thank you for watching so much. I really appreciate it. If you think this is interesting and you know someone else who likes math, please tell them. Let's get the word out. Okay, bye for now.